Good morning. All right, welcome everyone. It's wonderful to see all of you here. I'm Tsu-Jae King Liu, Dean of the College of Engineering. And it's really a pleasure for us, my leadership team and my development staff to be able to, and faculty to spend time with you this morning. So thank you for taking time out of your busy schedules to spend a Saturday morning with us. I'd like to extend a special welcome to the Berkeley Engineering alumni. Are you here, like bears, golden bears? All right. Welcome back. I hope that you've seen some, changes, positive changes here on campus since you graduated, and we're really excited to re-engage with you. And also the parents. It's been a pleasure in my new role as dean to meet so many parents who are so supportive of our current students. I'd like to extend a special welcome to them as well. All right, as you may know, Berkeley engineers lead the world in discovery and innovation to address grand challenges for our global society. And these include sustainable growth, human health and wellness, safety and security, and inequality. One of the hallmarks of our success here is a strong tradition of collaboration across disciplinary and organizational boundaries to develop creative new solutions to these grand challenges. So today we have the pleasure of having 4 of our distinguished faculty to share with us some of their most exciting research that's going to help shape our future. So I hope that each of you will be engaged, inspired, and encourage you to engage in lively discussion with these faculty after they give their introductory presentations. So I'll quickly just mention them right now, and they'll come up one by one. So first is Alex Bayan. He's a professor of civil and environmental engineering and also of electrical engineering and computer sciences. He's actually the director of our Institute for Transportation Studies. Second, after Alex, will be coming up is Amy Herr. She's a professor of bioengineering, and she's the faculty director of the UC Berkeley Baker Fellows Program, which fosters faculty entrepreneurship in the STEM fields through competitive grants. Next, we have Cara Nelson. She's a professor of civil and environmental engineering, and she's my associate dean for equity and inclusion. And finally, last but not least, Ikhlaq Sidhu. He's a founder and faculty director of the Sitarja Center for Entrepreneurship and Technology, and he's also a professor in the Industrial Engineering and Operations Research Department. So to begin, I would like to ask each of the faculty members to come up and give a short overview of their research. They're going to share with us what they're most excited about. And then afterwards, they'll sit down and we'll have a brief panel discussion. So may I ask Alex to come up and get us started?
Thank you. Good morning and welcome. So today I'm going to talk about the future of transportation. And all of you have probably read or seen on TV futuristic Star Wars-looking style rendering of what the future might look like, whether it's a new city in the north of Saudi Arabia like Neom, which is going to be completely automated, or whether you've seen CarTube or the Boring Company, not so boring, but boring as in tunnels, Hyperloop, and so on. But the real question that many of you probably have is, in a world where all the cars are self-driving, or part of the cars are self-driving, are we heading towards a better future or not such a great future? And this is a chart that the US Undersecretary of Energy, Ruben Sarkar, used to show that in a world where all the cars are automated, the energy footprint of transportation could go down by 60%, which would be a phenomenal future, or it could go up by 200%. In a case where you're sending your empty cars to pick up your kids from school, and we have freeways packed with empty cars, or a city with empty cars turning around looking for a parking spot. And that is a possible future. And so the work we do at Berkeley aims at steering us towards this minus 60%. And the one problem I'd like to talk to you about today is how we use self-driving car to make traffic better and specifically reduce traffic jams. Do we have anybody from Ohio here? Okay, good. We have one person from Ohio on our faculty. So in 1935 is the first time ever humans measured traffic. It was in Ohio because there was a tractor farm that did an agricultural festival, and there were maybe a couple hundred cars that came, and 100 cars were enough at the time to jam the small streets and the small roads of Ohio. That spearheaded thousands of articles in research in measuring traffic to understand the causes of the problems linked by traffic. In 2008, many years later, an experiment celebrated since the last 10 years was conducted in Japan, in which people were asked to drive at 25 miles an hour in a circle. A simple task, you would think. But what you see happening after a few seconds is a collapse of traffic, because humans are not able to maintain distances. But it's not that hard. I mean, how many of you have a driver's license? Come on. Yet, this is Japan, very civilized and disciplined country, you know. So the point here is that this is the cause of a lot of energy inefficiency in traffic. Now, 10 years later, a Cal grad, Dan Work, now a faculty at Illinois and now at Vanderbilt, did this experiment, same experiment. And what you see here, I'm going to just pause the movie for a minute. This is the same experiment. There's an arrow here. The arrow is a self-driving vehicle. Right now, the autopilot is not engaged, but at some point, the arrow will turn red. That means now the car is self-driving, and you will see what happens. The curve below is the curve of okay, hold on, this technical problem here. Okay, let's try that again. Okay, here we go. So this is obviously accelerated because otherwise it'd be boring. So right now the car is just driven by a human, and you can see after a while the same oscillations happened. 10 years later, still people don't drive better. Okay, so you see it happening right now. Okay. All right, now we're going to engage the autopilot. Okay, now it's self-driving, and what do you see? Suddenly things smooth out. So 42% energy savings. Whoops. 42% energy savings with that algorithm. Now, think about it historically. You know, 1935, first measurements of traffic jam. Thousands of articles of research. 2008, that first experiment to demonstrate some of the causes of the traffic problems. 10 years later, one guy, Berkeley grad, grabs all that research, manages to show that you can smooth traffic. Now, here's another interesting thing that happened 1 year later. Cathy Wu, another grad from Cal, who is now a faculty at MIT, comes along and uses machine learning to do the same. So now this is a simulation. We're going to test it pretty soon. So right now the car is not self-driving, but pretty soon it will, once it crosses the quadrant here, it will start to self-drive and smooth traffic. So you could wonder, what's the difference between this and the previous case? It's doing exactly the same it was doing before. The difference is the intelligence in the car. And let's just think about this for a minute. So it took about 10,000 research articles to come up with a good way to model what's happening inside the car and make the car stop the oscillations. Okay, and probably 100 of them or 1,000 of them were done between that first experiment and that second experiment. It took one article to remove all the mathematics models, the years and years and decades of people trying to model what's happening inside the car, and just have a computer learn it. And the computer not only learned it, but it did better than the human. So you could argue that these tens of thousands of articles that were written in the past are almost useless. And that's an interesting paradigm, because this is the beginning of a new era. I'm going to show you a few other Lego blocks of how we're going to make this work in the future, in which every time the same color scheme is used, you have a self-driving vehicle. It can measure, so that's the red vehicle. It measures what's happening with the blue vehicles around, and it doesn't see anything on the white vehicles. So first thing is, now, let's do 2 lanes. You can see this guy is behaving kind of like a jerk, right? It's switching lanes to prevent people from passing. But it actually stops the problem. No human ever managed to derive an algorithm to do that. Now the computer learned to do it with machine learning in a few minutes. And you could argue, well, what's the big deal? You learned this in police academy, right? So, you know, maybe the computer just relearned what you learned in police academy. Okay, now try this one. You know, like a typical stop sign in California where people are polite. Please go. No, no, please, you go. No, please go, you know. Okay. So now, what did the computer learn? It learned to create a snake. It doesn't know what a snake is. Obviously, it's a computer. Okay, but it learned to do it without any model. So there's no more math. It's just artificial intelligence. And I can still explain to you that's a snake. I can explain to my daughter, who is in the back, who's 10 years old, that's a snake. Now this is what's happening if no self-driving vehicle happens. You have a bottleneck, people are merging, and this is not very efficient. And now we ask the computer to learn what to do with this. What it does is going to show here. I can't tell you what it's doing anymore. It sometimes will hold cars. Sometimes it will let them go. But I can't even rationalize what it came up with. And you can see this is the frontier of intelligence in the sense that the previous cases were rationalized and solved by humans. This one, humans can't solve, or at least have not managed to solve it. And even if you presented a solution, they can't even explain the solution anymore. But you look at the numbers, it's actually more efficient. So where are we going with this? And we can do more things. Like then you can say, you learn on a ring, and you try it on a merge, and it still works. So there's a lot of things you can do with it. Now, where are we going with this? And this is something that your children will see in their lifetime at Berkeley. The next thing is, what about the Bay Bridge? There's right now a big metering light that prevents cars from entering. What if instead you had self-driving car holding the flow so it flows smoothly? This is a reality we will collectively experience within less than 10 years guaranteed. That's one thing we would like to demonstrate pretty soon, and maybe in the lifetime of your children while they're at Berkeley. Essentially with a philosophy where intelligence and artificial intelligence enables us to solve small Lego blocks. And if you assemble the small Lego blocks, you might be able to solve much more complex problems, such as the Bay Bridge problem on which we're currently working with the California Department of Transportation. We don't know if we'll be able to demonstrate that because that's a very security-sensitive point. But one thing we will do by 2020 in Los Angeles for the ITS World Congress is work on situations which are way more complex, like the I-210 corridor. If there's anybody from LA, you'll recognize that. If there's anybody from LA, you'll recognize that, and be able to react to complex accidents, such as 3-lane closures created by truck accidents. So the point here is this will happen while you are at Berkeley, where the generations of students who just came in are at Berkeley. That will happen within 2 years. And within 10 years, hopefully we'll do a lot more ambitious things like this one, which is my last video. And then I will give it to the next speaker. So hopefully this gives you a glimpse of what the future might look like. Maybe some of you have seen this already.
Bring me a dream, making it cute and you'll have nobody to call my own. Please turn on your magic beam. Mr. Starlight, bring me a dream. Mr. Starlight, someone to hold. Would be so busy before it's too old. So please turn on your magic beam. Mr. Starlight, bring me a dream.
Go Bears!
Good morning. It's a pleasure to be here. Welcome, everyone. My name is Amy Herr, and I'm a professor of bioengineering here at Cal. I'm going to take a couple of minutes to tell you a little bit about the research that's going on in my group. And to begin, I'm going to ask you to take a look around. I think after that video, it makes a lot of sense to look around. But in the work that we do in bioengineering, we look around for other reasons. I think if you look around, you'll see that we all look pretty different on the outside. It is true, however, if you take a look at the inside, at the genomic level and the level of DNA, we're all pretty much the same. In fact, we as humans are all almost exactly the same. So there are other things that we have in common. Unfortunately, we all get sick. Sometimes we get a fever or a stuffy nose or a sore throat. When we start getting sick, those changes that are happening on the outside, those symptoms that we see, are oftentimes happening much earlier on the inside as well. Those changes can be temporary, they can be fleeting if our illness is something that's minor. If we are, however, afflicted with something that's more serious, those changes on the inside might be more permanent. But those changes, whether they're temporary or they're permanent, at the molecular and the cellular level, they oftentimes happen before symptoms start appearing. And this is exactly what my research group does here. We take a look at different molecules and cells inside of individuals by developing new measurement technologies so that we can inform new diagnostics and new approaches to clinical medicine. there has been a huge advance in terms of understanding molecules and their links to disease. The Human Genome Project is one perfect example where measurement science made a big difference in terms of being able to link those measurements and those changes at the molecular level to clinical implementations in diagnostics. So if we look at on the left of the screen, you'll see an image of DNA, and that's a molecule that's really benefited in terms of our understanding. On the right of the image, however, is a molecule that we know as a protein. So a protein is created by the information that's housed in the DNA. These molecules are really intriguing. They're very dynamic, they're very vibrant, and they oftentimes can actually reflect more what's happening in our body than DNA. So one way to think about this is on the left side, the image that I had of DNA, the genetic code. You can kind of think about that as a blueprint, and that's what that little schematic is there, a blueprint on which we base our plans. On the right, if you think of DNA and the genetic code as a blueprint, on the right, you can think of proteins as literally molecular machines. So these dynamic, ever-changing machines zip around the architectures that are encoded in blueprints. They modify those architectures, and sometimes they build those architectures as well. So DNA may be a little bit more static than these molecular machines that we're interested in, something that we call proteins. Proteins are really interesting. There are literally millions of different forms of proteins, these molecules inside of each of our body. So that presents two aspects. On the one side, that's a monumental opportunity for measuring molecules and understanding how they link to disease. On the other hand, that's a really big challenge. So the opportunity comes from the fact that these molecules are dynamic, as I mentioned a moment ago. So they really have a good reflection of the current state of the body. They can reflect both how disease is progressing and also how healthy you are. They can also provide a window into how your body is responding to particular therapies. So we're quite interested in using proteins as these biomarkers that I mentioned earlier. The flip side of the coin is there are so many of them. And that is really a monumental challenge. How do we tease apart these different millions of different forms of these biological molecules to link them to a specific disease state so that we can develop accurate and effective diagnostics for clinical medicine? So you can think about the work that we do in bioengineering and my lab here at UC Berkeley as developing measurement tools to study molecules inside cells, sort of a stethoscope for the cell, if you will, bringing a new era of precision to medicine so that we all might benefit. This is a big challenge, as I mentioned a moment ago, but it's also actually quite a tiny challenge. Some cases of disease, like cancer, for example, had a lot of variation between cell to cell, cells within the body. So cell-to-cell variation and heterogeneity can be really important. This is an artist's rendering, but it shows here a mammalian cell, in this case a red blood cell, sitting on the tip of a pin. So you can see just how tiny these packets of life are that we're interested in analyzing with precision. In this particular case, these types of cells are literally 1/1000th the volume of a human tear. So a very small amount of life packed into that little packet as well. Luckily, we're able to make measurements of molecules inside of these tiny cells thanks to something that you actually brought with you today. So if you have a backpack or a purse or maybe in your back pocket, a cell phone or a laptop or some kind of a tablet, those chips that are inside those devices that for you are routing electrons and information, some of which was invented right here at UC Berkeley. This is a photo of the Marvell Nano Lab, a place where a lot of these inventions have come from. Those chips that you have that are routing electrons and information, we adopt and then adapt. We hack those advanced manufacturing techniques so that we can then use those same devices to be able to route molecules and cells so that we can make these precision medicines that are linked to clinical medicine of the future. This is just an image of the type of chip we have. It's a planar device, a flat device. We use these tiny little microcups that are about a diameter of a human hair in size across to isolate and manipulate individual cells, cancer cells, for example. And again, we use all of the processes that have been developed for the integrated circuits that you're carrying with you. So I love to talk about measurement science, but I also love chocolate. And there is an interesting overlap between those two seemingly different areas. So I put this image up here, one, because I like looking at it, but also because there's a similarity, and that is, especially in the case of the work that we're doing on cancer and analysis of individual cancer cells, sometimes the outside of those cells, between two different cells, looks exactly the same. Much like when you eagerly open a box of chocolates, you might see the outside chocolate surface of those different chocolates looking very much the same. Now, for those of you who really don't like the coconut chocolates, you may understand how important it is to know what's inside that chocolate before you take a really big bite. And that's exactly the same type of information that we're looking to report. These cells are oftentimes very similar on the outside, but the insides can be very, very different. And the inside is what holds the proteins that I was talking about earlier as biomarkers. So for us, the trick is, how do we take something like an intact cell, represented here with an intact egg, how do we break it open using these little microcups that I described earlier? And then we essentially use electrophoretic phenomena, some different types of transport, to be able to sort the different molecules that are inside the cell to understand what's happening with those biomarkers. And we do this using, again, those advanced manufacturing processes I mentioned a moment ago. So I have just two things I want to say in closing. One is, we're really interested and work very hard to push the frontier of understanding and knowledge. This fundamental science that I would argue is really only enabled through engineering and tools development, measurement science. I've had an opportunity to be involved in a couple of different startups, including from undergraduate courses that I teach here at Cal. But in addition to that, research from my lab has spun out into the world, which is a journey that was quite interesting to be able to see the technologies that you once thought weren't possible now get into the hands of people across the world. And as an engineer, I think there are almost no greater joys than seeing something like that. But there is one greater joy, and that is being able to see the students and scholars who are here transition from being a student and scholar into being leaders in business and the world around us. This is Dr. Kelly Gardner. She's a Cal alumna. She graduated with a PhD from my group, and she was CEO of our startup. I say was because the startup was acquired under her leadership. So seeing things like that are what makes Cal really, really dynamic place to be. You probably already know that we're the #4 global university, the #1 public university, but you may not be familiar with some of these statistics. Forbes magazine ranks us as the #1 startup university, and PitchBook this year named us as the #1 university for entrepreneurs. So if you or members of your family or people are interested in trying to start a new effort or maybe joining a new company, there is no better place to be than UC Berkeley. So with that, the overall focus of the research that we do in my lab is how to bring together engineering with biology to impact clinical medicine in a way that will allow us to see humans with precision, both at the molecular and cellular level, as a means to inform precision medicine. Thank you.
Wow, this is so fun. I wish the start of every school day was like this. So, my mic, yeah. So, again, I'm, excuse me, Cara Nelson. I'm an alumna of UC Berkeley. I got my BS degree here in 1992 in biophysics. And it took me a few years to see the light and come over to the engineering side, where I'm now very happy practicing in my field of environmental engineering. And I wanted to start off by sharing a tiny bit of history. So environmental engineering grew out of the field of civil engineering. So our department now is called Civil and Environmental Engineering. And civil engineering was one of the 6 original colleges established when UC Berkeley was founded in 1968. And water is one of the main reasons that Berkeley was founded on its location, the location that we're at, because Strawberry Creek, which flows out of the East Bay Hills and actually there are 2 branches, they joined together at the very bottom of campus, was the original water supply of UC Berkeley. And so it has everything to do with why we're here. But what happened to Strawberry Creek over the next 150 years is pretty interesting. It moved from being our water supply to our sewer. So originally, all of the waste that were generated on campus, not just in our bathrooms and from our sinks, but from our laboratories, were dumped directly in Strawberry Creek. And so it changed over the next 50 or so years to being our sewer and our dumping grounds and an eyesore and a smell, a source of odors. And so it wasn't until the mid-1900s that the tides began to change and people started asking, why did we let this happen? What happened to this amazing resource that we have right here on campus? And it was many decades of work. There were collaborations between faculty, students, and staff that returned Strawberry Creek to what it is now today, which is one of the jewels of our campus. And that's been a very successful effort. And it actually mimics, in many ways, what's happened in my field of civil and environmental engineering. So civil and environmental engineers, in terms of the work that we do with respect to water, originally, our charge was to deliver drinking water. Originally, we just took water straight out of the environment. We didn't provide any treatment, and we provided it to our human populations. Then that water started to become contaminated with human waste. We realized we needed to treat it. Then we realized that the waste that we were discharging into the environment were causing harm, so we started treating our waste before we discharged them. And that brings us all the way to the present, which is our view now is that these wastes are not waste, they are resources. So our view now is that water is infinitely recyclable, and anything that we put back in, we can take back out, and we can capture those as resources. Another reality that we now face, especially in California, is that water is scarce. So all of this massive infrastructure that has allowed our state to thrive, become the economic power horse that it is, involves massive transfers of water, of surface water from the Sierra Nevada west and from north to south. Those are no longer reliable in the way that they always have been due to climate variability. Most of our groundwater basins that we pump in order to provide water for irrigation, as well as our cities, are overdrafted, many of them critically. There are some parts of the state where the ground is sinking as much as a foot per year because we're pumping the water out too fast. So what are we going to do about that? I'm fortunate to be part of a center, an NSF-funded center, called Reinventing Our Nation's Urban Water Infrastructure. And we do not feel that small, incremental solutions are going to get us to where we need to go, to the water infrastructure of the future. We're really relying, in most cases, on technology that was developed over 100 years ago. We haven't made this leap forward that's taking advantage of some of the innovations that you heard my colleagues talking about yet. So we are roughly, the main charge of our center is to reduce the cost and environmental impacts of our water infrastructure while increasing its reliability and adaptability. But it's hard to innovate when your job is providing safe drinking water, because you can't afford to have errors. You can't afford to deliver water that's unsafe, even for a small moment. So the field that I'm part of is very naturally conservative. So one of our challenges is trying to create a new way of thinking about innovation, create this innovation ecosystem that's going to allow us to invent the water infrastructure of the future. Part of that reinvention at ReNUWit, we believe, involves the practice of potable reuse, where we take wastewater, we're talking about everything that goes down a drain, not from industry, but from in buildings and in homes and in businesses, and we turn it directly back into drinking water. We see this as unavoidable. We just don't. We can't afford to send that water back into the environment and not reuse it again directly. So there are a few different flavors of potable reuse. The two on the bottom involve taking that treated wastewater and putting it back in the ground so we can recharge our aquifers that are being overdrafted. We could also take that water and put it in a reservoir. And that's happening already. The practice of recharging groundwater has been occurring for over 30 years in California, and you can see in red dots cities that already rely on that practice. In blue, you can see cities that are planning to implement that practice in the near future, and in green, cities that are planning to start augmenting a reservoir or some kind of large storage basin with treated wastewater, which we call purified water. This last practice, the top loop, where we take wastewater, okay, so here's your homes. We've got a wastewater treatment plant here. That's what we usually do, but to all wastewater in the US. But it goes to this advanced treatment plant, and we now know that we can treat that water to the point where it's so pure that we can send it directly back to your homes. Now, this practice is not yet legal in California. It's legal in Texas, and there are 2 cities in Texas that have started doing this. But California is going to follow shortly in their footsteps. So I was fortunate to be part of an expert panel that provided input to the state of California. We worked for 2 years, drawing on expertise from all across the country to assess the state of the science and give our state regulatory agencies the confidence to move forward with developing regulations for this practice. So this is now happening, and this practice will become legal in California in the year 2023. But we still don't know everything that there is to know about how to ensure that this practice is as safe as it could possibly be. It's very complicated, and so there's always new science, new engineering that we can be bringing to bear to continue to increase confidence in this practice. So my research group specifically has been involved in studying 2 facilities that are testing this practice. So one of them is in El Paso, and we did work at, this is a pilot scale facility where they were testing all these different advanced treatment processes. And then we took some of that treated water and brought it back to the laboratory to continue to do experiments with it. And we've also been working in San Diego that has an even larger demonstration facility, and then took that treated water and sent it through pipe loops, which attempt to simulate what happens between the treatment plant and your home. So your water goes into this complex network of pipes, and we need to understand what happens to the quality of the water when that process is occurring. So one of the emerging techniques that we have been employing to bring new science to this practice is the ability to sequence all of the DNA in a sample, and in our case, our sample is the water. So water is never sterile, or if you sterilize it by boiling it, for example, it never stays sterile for long. Bacteria grow everywhere. So we call the consortium of bacteria in water the water microbiome. And so we're now using these next generation sequencing tools to sequence all of the DNA in a sample, and we can do this at different locations in the treatment plant, at different locations in the pipe system that we've been simulating, so that we understand what changes are occurring all the way from raw wastewater back to your household tap. So if you look at this diagram here, each row represents a unique DNA sequence that we found in one of the water samples. And as you move from left to right, you move from raw wastewater up through, these are the different treatment steps, and up through our simulation of the drinking water pipes. And one thing that you notice is that the sequences that are present over here have almost no overlap with the sequences over here. That tells us that the microbial identity of this water has completely changed. We also look at the chemical parameters that are in this water, all the different chemical compounds, thousands of chemical compounds that are in this water, to demonstrate that the raw wastewater that we started out with has nothing to do with the final purified water that we produce through all of these advanced treatment processes. But there is a concern. Is it possible to make water that's too pure? Like, we don't actually want pure H2O molecules going into our pipes. If we do that, they will corrode and release potential things like lead. They won't actually be healthy for you to drink. You need electrolytes when you drink water. And if we don't have microorganisms in there, we don't know what might grow if we're not controlling the growth conditions. So our aim is actually to produce water at this point that is stable from all of the different types of parameters that we can think of, and the water microbiome is one of those parameters. We want to deliver healthy water like humans have been drinking for thousands of years, out of the ground, out of a natural spring. That natural spring water that we've been drinking for thousands, tens of thousands of years is chock full of microorganisms. It has its own natural microbiome. So where I see this field going is here. This is the disruptive technology that I believe environmental engineers have to offer. This is actually my son. 5 years ago. This is a display at the Auditorium Museum, our world-class interactive science museum over in San Francisco. This is pretty good. You can see this. So there's a drinking water fountain coming straight out of a toilet. This is that practice of toilet to tap that usually has a very negative connotation. Where I see us going is that we will have so much confidence in our ability to deliver safe water through this practice that this will become a preferred water source. People will have even more confidence in recycled wastewater and purified water than in your conventional tap water that you've grown up with. Thank you.
That's the point where I'm starting this talk. Let's point that out right now. All right. So clearly we have a set of innovators here. We have innovators that come out of Berkeley all the time. What I want to bring up to you, just this question. We started this question 14 years ago. That is, can you actually, first of all, yeah, you can teach people skills, right? We do that all the time. We teach people, every discipline. But can you teach a person to actually have innovative skill, like innovative behavior? Can you teach them to be an innovator? Can you teach them to be an entrepreneur? That's the thing that we've been trying to figure out for years and years through the development of the program that I'm part of. So to start that, let me just say, if you can do it, you can't do it this way. Is that fair? Like, you can't do it teaching it just the same way that you teach all the other subjects, particularly like math and science, because when you're starting something new, when you want to create something new, there's not a formula for it. You're doing it in a new time, new space. You can't copy something before. Like, something has to be done completely new. And if you're going to teach it, you can't just test that they read something from a book and repeated it back to you. That doesn't mean that you can figure out new things or you can make new things happen, right? So if we can teach it at all, how could we do it, right? What can you do? And this is the slide that I want to explain our belief system in whether and how you can do it, all right? So you take, the background on this is we used to think, oh, you just teach some business classes to people who are in engineering and somehow they'll figure, everything else will just solve itself, okay? So we've grown beyond that, right? So this slide here, the vertical axis is, or put it this way, everybody in this room, every student, you can map them somewhere in this slide on these two axes. One axis is how good are you in like a particular discipline or a skill? Like, how good are you at computer science or finance or any particular topic, right? And universities, and this one is maybe better than all the rest. I just had to throw that in. At taking people who have a lot of potential in a particular skill area and making them even better in that skill area. So we take people who are really smart in the area and we make them better. We put them higher up on that vertical axis. Let me see if I can point it all here. I don't know if I can. There. Yeah. So it's like being here and going up higher, right? There's another skill people have, and you can think of it kind of like being street smart, okay? It's a broad skill. It's knowing who to talk to get something done. How do you talk to them? Did you actually hear what they said when they talked to you? What do you notice in the world? How do you see what's going on, right? Those are all broad capabilities, right? And so people who are good at that, they can be way out here. They can be effective. They can actually do well. Sometimes they're not strong in the other dimension. They're just street smart. But and organizations, by the way, are full of places where everybody is like this. Smart and a little bit narrow. And you know what you are if you're just a little bit broader than everybody else in the organization? You're the vice president. Right? So the person who's just a little bit broader, basically they're not the leader because they're the smartest person of everybody in the company. They're the leader because they're about as smart as everybody else in the company, but they had this extra broad capability of how to interact with everyone else, how to see the things that other people didn't see, how to get other people to help them do those things. And so what we're doing is we're taking the students who are here, who are very smart already in this category, and we're pushing them just to the right a little bit, and maybe some even more. And if you can get all the way out here, you're just not the vice president. This is like being Steve Jobs. This is, if you have these very broad, smart, innovation, behavior, mindset type of capabilities, and you're very smart in a discipline, that's being an entrepreneur. That's being a really great innovator. That's our goal. Okay, so this is the main point, actually, I wanted to tell you. All the rest of these slides are background after that, all right? Okay, but this is the point here. So to go along with that, we can actually teach people to do this. That's what we've been figuring out how to do for all these years. I'm not going to go into the exact detail of it here, but I'll just say we can stretch people like you stretch them in therapy, all right? Not just in class. You can stretch them, and you do it in situation. While they're working on the project, while they're working on the company, we're developing them as people. They can reflect on how they're developing as a person and with the decisions that they're making for the project or the company or whatever it is. We can even teach these behaviors in very technical areas. So this is a class. It's called Data X. It's something that I started to work on about 2 years ago. Nobody who takes this class believes it's a behavior-related class. It's completely technical. It's a refactored data science class. You can see the kind of projects that people can build within 3 months. It has all the theory, state-of-the-art machine learning tools, and a wide-open project. People are detecting fake news. They're predicting energy prices. They're doing everything that you can do with machine learning and AI. And secretly in there, we're also getting them to have innovative and implementation-related skills so that they can actually make these things. They don't just understand the theories disconnected, but they can build this in 3 months with no starting point. A starting point. They know Python before they start, but not knowing machine learning before they start. All of this, I'll just say, we have impact. We've been doing this for a while. It's worked. We have a list of companies. Many, many students get together. They kind of learn these behaviors, these mindsets, and then their startup gets acquired by Facebook for $100 million. Another company is I have a long, long list of companies that have come out of here. But the goal is not only to start companies. Like I said, if you have these extra behaviors, you become the leader in wherever you go. It doesn't have to be about starting a company. This year in November, on behalf of everybody at Berkeley and on behalf of all the great people that work in my center and so forth, I'm receiving the IEEE Major Innovation Award for IEEE Major Innovation Award in the engineering category. That's just coming up, but that's somewhat testament to what we figured out how to do here. I can tell you, people from all over the world, like every continent, universities everywhere, they come here to see how can we actually get people to learn these things. And so I'm just going to somewhat end this by saying we can. We think we figured it out. We can do this. And we've been doing it. State of the Center today, it's not 2 classes. It's relatively large, 12 to 14 classes every semester. We have about 1,500 students or more that are taking these classes. We have labs and executive programs. We have like a different version of this. People at Apple, Google, Yahoo, Network Appliances, Samsung, Cisco, like all of the Silicon Valley companies that you think of, they come to our programs to also learn versions of these things. Global partners, 14 global partners all over the world, same thing. It's not a small activity anymore, I'm happy to say. And anyway, so I'm going to end it here. This is our final story, which is basically we teach people to have a particular mindset and a behavior, and then we put them in actual innovation situations by mixing people that would never meet each other. And this is basically the formula for what the center is, and we've kind of become an innovation collider. It's kind of another word for a very different type of accelerator. Okay, all right, thank you.
All right, thank you very much. I think hopefully you all got a great sense of what's coming down the pike in the future. I'd really like to thank our outstanding faculty for giving us a vision of some things that we can look forward to, and to share with you how we are actually preparing our students to become leaders of the future who will actually build it. In the interest of time, because I'd like to give you all a chance to ask questions, I'll just ask one question of the panel, and they can answer it as they feel free. Since this is homecoming weekend, and we have a lot of alumni who are returning, and as well as parents of current students, maybe I'd like to hear from you. I think each of these faculty have been here for quite some time. How do you think has Berkeley engineering, or Berkeley, has changed in recent years, and so that might be different than what the alumni here have experienced? And I assume this is all changing in a good direction, but yeah, maybe just from your perspective as faculty, how do you think Berkeley has changed for the better at Berkeley engineering, and how that's going to help make broaden our impact and help to make the world a better place?
I have definitely seen, so I've been here 11 years. I've had the honor to work with hundreds of undergraduates and a smaller number of graduate students. And I would say maybe two things. One, just the scope of collaboration in terms of our Cal students, undergrads and graduate students, which was probably the case when our alumni were here as well, really thinking about not only how much can I learn, but what can I give to the world through this experience. And I think the scope of collaboration I've seen expand. And I've also seen that expand outside of scholarship alone. So close working with nonprofits, close working with companies large and small, and close working with other individuals from across the world as well. Those are two things that I've seen change.
Completely echoing what Amy just said. I think the one thing I've seen changed a lot in the recent years is I think Berkeley has taken over the world for machine learning and artificial intelligence. I think we just have become the leader. It's just a complicated phenomena of coexistence of a lot of different factors that contributed to the explosion of the critical mass of faculty working on this, and the amazing set of applications, going back to the cross-disciplinary component of it, essentially enabling machine learning to permeate in every possible subfields of civil engineering and bioengineering and mechanical engineering and so forth. And I think that makes us an absolutely unbeatable place right now in this domain.
I'll just add one additional element which I really see, which is I think Berkeley has always been a place where we care a lot about the impact of our work, but I've seen a real transition in my 18 years here so far in that I feel like when I first arrived, the emphasis on scholarship, so for our faculty and for our graduate students, was on just advancing knowledge, and now there's more focus on ensuring that that knowledge that you're advancing is connected to impact. So are you doing research not just for research's sake, but research to make the world a better place, and not 100 years from now, but now?
All right, so I'll add to that. First of all, there's an obvious change. If you've been walking around here, have you seen the number of new buildings? And when I came here, that Citrus building next door was a giant hole in the ground. I mean, for years, it was just an empty hole. And since then, I've seen just a tremendous amount of growth in literally every area, every discipline, the infrastructure. There's been a lot happening. So at the physical level, I think all of those things have happened. I think there's another thing that's been happening, which is the connectivity of the university. It was always good. Like, I don't want to give the wrong impression, but the number of people that we invite in and the number of ways that Berkeley faculty are sitting on the boards and connected into things on the outside, I think that's really increased. And it's because it's somehow culturally, kind of this idea of, what was academically okay from a narrow sense, but realizing that you really have to connect into the rest of the world, and it's become culturally acceptable and promoted to do that. And out of all those interconnections, I think that whole innovation and entrepreneurial culture has also just incredibly expanded. So I think not just the physical infrastructure, but our kind of reach into the whole world and the whole world's reach into Berkeley has increased.
Excellent. Okay. Okay, at this point, I'd like to open it up to questions. Maybe we're going to be passing around the microphone just to help people who might not be able to hear it as well to hear your question clearly. Please introduce yourself and ask your question.
I have a question about innovation and entrepreneurship. How far out in terms of the number of years do you follow the performance of graduated students in order to validate your assessment, your methods, and your set of metrics shown in your last slide? After all, startup success probability is very, very small. It's less than 10% success. That's my question.
Okay, all right. I'm going to assume that question's for me.
Me too.
You guys are welcome to answer it if you like. So it's a really good question. Doing a long-term assessment, it's a very difficult thing. It's something that we've always wanted to do. It's really hard to track. It's really hard to track people as they get farther and farther out of school. I mean, we're lucky if we can still send them an email, let alone, figure out what are all the things going on in people's lives. And frankly, there's two arguments to this. One argument is everyone who comes here, they're just so incredibly smart and good, and they've been selected so carefully. Maybe we don't need to do anything, and they'll all just start companies, and and they'll just change the world anyway. And then out of that pool, you say, well, a whole bunch of people have started companies. Well, was it because of exactly this thing that we did, or was it because they were just so good? I'm going to say it's really a complicated thing to study, but I can tell you on a personal experience level, from the day we opened the center, I can tell you Mixbook, I can tell you all these companies that started even out of that very first class, and I know their stories. And we talk to them, and they will tell us how what they learned made all the difference. So I don't have the best answer, but I have a good enough answer. I feel good about it.
Maybe can I just jump on that and say a couple things. One is the assumption that we're only looking for success in the companies. We're not. As you pointed out, most of them fail. And that's part of, I think, what we teach here is that ability to take methodical, reasoned risk in terms of that. So that's one aspect. So we track it, but I wouldn't say from our perspective that the failure or success of the company is the bottom line. In addition to that, we do use new methods like LinkedIn and other ways to keep track of people. But a lot of them come back and act as mentors and coaches as well. And so for me, that's another metric is how can our alumni feel that they're contributing and how can we make those opportunities as well?
And in fact, just to echo what Amy said, there is a book one of our faculty wrote on how to recover from failure. It's called The Other F Word. You should read it. That is the title of the book.
A quick question for Professor Nelson. I think, hi. The groundwater question is so important for all of us. We live in the Northeast, and you might have heard of fracking and the Pennsylvania water catching on fire, et cetera. the technical, things are so important, but what about like the legal implications when, companies refuse to tell us, people get sick and go to the doctor and they won't tell us the chemicals that put into our common shared water? Is there anything we're doing on the, the legal or the other framework about what's in our water?
Yeah, absolutely. That particular practice of fracking is an example where the practice is still a little bit ahead of the science, and the science is racing to catch up. But there's a lot of work going on to better understand the potential implications on the water quality underground that may be in the area of influence, as well as other implications like increases in seismic activity. So there's a tremendous amount of research going on in that area. And then from a regulatory perspective, this doesn't address exactly the risk due to fracking, but California enacted landmark legislation 4 years ago to finally require all groundwater aquifers in the state to be sustainably managed. And so that is coming into groundwater basins have to start complying with that over the next 10 years. And so there are sustainable management plans being developed for every basin, starting with those that are most critically overdrafted. So I expect a much brighter future, at least in California, in terms of how we're sustainably managing those resources.
One more question. I think we have time for just one more question. Okay, there's a competition here. I know. Okay, sorry.
So this question is for Mr. Bain. I was wondering, you were talking about how the computers were making these advancements and things and helping the traffic run more smoothly, but I was wondering if there would ever come a time where the computers got so smart where they decided they didn't want to follow the rules of traffic, and they decided that, hey, I don't want to go this way, I want to go this other direction, but it runs into a problem where it potentially hurts somebody or they become too advanced and we don't know how to stop them?
So there's an episode of Silicon Valley where a guy gets in a self-driving car and then the car takes him to a container, onto a ship, into an island. So definitely a good thing to watch. There's also a lot of movies where Terminators start to exterminate humans. And the truth is, you're right. Cars could become weapons. In fact, three-letters agencies are working on that. Right now, I think a three-letter agency can take over your car remotely if your car is modern enough from within 10 meters and take it over. It's not that far away that someone could take it over from another country. And so I think this is a responsibility we collectively have when we advance these technologies, is that we have to make sure we embed in the research, in a sense, a fail-safe or a way to make sure that these dystopian developments we don't want not to happen. And it's going to be a constant tug-of-war in research, because you will have the hacker team that is working equally hard to your team to try to disrupt. I think we really have embraced that at Berkeley very seriously. There's even a center for AI for good, for common good. And we need to keep working at it. I mean, that's kind of one of the landmark of our university.
All right. Great question. Unfortunately, we're now out of time, and so I'd like to bring our discussion to a close and thank my colleagues for sharing their work with us. If you'd like to see what some of our Berkeley engineering students are up to, I encourage you to go visit Jacobs Hall, which is across the street. It's the home of the Jacobs Institute for Design Innovation, which is now hosting an open house. And I'd like to thank you once again for joining us today, and enjoy the rest of the homecoming weekend. Go Bears!